So without further ado, I'd like to invite Yue Xiu Peng, Senior Manager, ST Engineering, to present DigiShip, digitalization of ship operations. Xiu Peng is a Senior Manager in the Department of Automation and Electrical Systems under the Division of Engineering Design Center at the Marine arm of ST Engineering. She's involved in the design and development of the NERVA ship management system at ST. Prior to ST, she was the deputy head in the Group Technology and Operation Ops Center at Certis Group. Xiu Peng received her MSc in System Engineering at Naval Postgraduate School and MSc in Defense Technology and Systems at NUS. She obtained her BEng in Electrical and Electronic Engineering at NTU. Xiu Peng is also a certified project management professional and a certified ITIL specialist. Welcome, Xiu Peng.
Hi. Very good morning to everyone. My name is Xiu Peng from the Marine arm of ST Engineering. And I'll be sharing with you on the topic DigiShip, digitalization of ship operations. Okay, this is the outline of my presentation today. So first, I will touch on the concept of DigiShip and the foundation pillars of DigiShip design. So I will also introduce on the NERVA ship management system and sense-making system, SMS², where platform machineries and sensors on board the vessels are connected to. This allows operators to remotely control and monitor platform machineries and sensors from the bridge, or monitor them from an operation station that is on the shore. Then I will share on a case study on the remote connection to the shore command center for autonomous tugboat through local telcos 4.5G network for operations in the coastal waters of Singapore. Then I will share on a systematic approach for security assessment of the NERVA SMS². Last but not least, I will share on the achieving smart maintenance through condition-based maintenance in the DigiShip design concept. So the DigiShip design concept aims to design and build future-ready smart platforms through digitalization of ship operations. There are 5 areas of focus in the DigiShip concept on how digitalization can change ship operations. The DigiShip shall be a one-stop data shop that has an integrated data lake for aggregating data from all shipboard systems to support the crew operational and maintenance duty. Through the use of advanced analytics and to optimize the maintenance efficiency, ship crew can be equipped with digital assistant tools to assess various know-hows. The DigiShip shall use automated system to perform tasks to achieve a no hands-on-deck concept. Full connectivity enabled by wire and wireless networks infrastructure on the DigiShip sets the foundation for the use of smart sensors and smart equipments, giving rise to the Internet of Things at sea, allowing crew to communicate and perform tasks remotely. DigiShip shall also be a multi-purpose enhanced mothership that is able to carry out many types of missions and control many unmanned assets. The green ship pillar of DigiShip is targeted at reducing greenhouse gases emission through hybridization and use of alternative fuels. Increasing energy efficiency can be done by optimizing the hull form of the ship. A model-based system engineering approach for ship design can facilitate simulations for optimizing of the hull design. For connected ship capabilities, situational awareness on board the ship can be enhanced through ship-wide crew location tracking, and centralized monitoring and control and management of ship platform systems. Secure onboard Wi-Fi, ship-to-shore connection with cybersecurity protection will allow remote monitoring and control from the bridge or from a remote shore control station. Smart maintenance uses data analytics and machine learning techniques to reduce the lifecycle cost of the ship. Prognostic alerts on potential machinery failures can be coupled with customized decision support for proposed maintenance action for the operator. By shifting to a condition-based maintenance regime, unplanned downtime and its associated costs can be expected to reduce. With automation technology, the crew will be able to perform a wide range of tasks with minimum human intervention. Additionally, berthing of the vessel can be performed autonomously. Automated mooring systems can also be used to complete the end-to-end berthing operations with minimum crew involvement. So the Vanguard 130D is ST Engineering's proprietary Vanguard series hull form. Based on the design concept of DigiShip, Vanguard 130D is packed with the latest innovation to harness the multiplier effect offered by digital technologies. The Nova Ship Management System. The Nova Ship Management System and sense-making system provide centralized control and monitoring of platform system and sensors. Leveraging on the data collected from platform systems and sensors on board, Nova is incorporated with data analytics technique to perform equipment health monitoring and predictive diagnostics. Nova is further enhanced with a decision support engine, which provides recommendations of required preventive actions to the operator. This allows for a condition-based maintenance approach, which will reduce unplanned downtime and maintenance costs. For the vessel that operates along Singapore coastal waters, network connectivity with a shore command station could be achieved through 4.5G private APN network with the local telco. I will share on an autonomous tugboat project which maintains a continuous ship-to-shore connectivity for the shore command center using a 4.5G network. The data transfer between the autonomous tugboat and its remote shore command center includes navigational waypoint plotting from the shore, the navigation status of the autonomous tugboat, the tugboat platform system statuses, and the streaming of video footages back to the shore. So this is a photo of the autonomous tugboat that was used in the project. And this is the photo of the shore command center. The trial site was at the Raffles Reserve Anchorage. Some optimization by the local telco was done to enhance the coverage at the trial site. So with the mounted antenna at the mast of the tugboat and the optimized coverage at the trial site, the network connectivity and performance at the designated trial site was good. So I will share on some of the observations from this project on the 4.5G private APN network for maritime applications. The bandwidth requirement for the transmission of data between autonomous tugboat and the shore is about 6 megabits per second. So with a private APN network, maximum bandwidth of 10 megabits per second, the 4.5G private APN may not be able to handle multiple autonomous tugboats. So it was observed that there were interruptions to the network connectivity when large vessels go in between the local telco transmission base station and the autonomous tugboat itself. So it is also observed with a 4G coverage en route from the shipyard to the trial site was poor. So though it was noted that there are scenarios that 4.5G from the local telco may have its limitation for maritime applications, it may be still suitable for non-critical and non-real-time control of the maritime autonomous service ship. So, and with the introduction of 5G network in Singapore, there will be another option for connectivity for maritime applications. For cybersecurity, in this section, I'll be sharing on the work done to systematically identify attack surfaces and possible threats and vulnerabilities for the Nova Ship Management System and sense-making system. So the methodology used for this security assessment includes system review, threat analysis, risk assessment, and security control recommendations. The cybersecurity assessment framework, STRIKE, and Heaven's methodology are applied for threat modeling and risk assessment, respectively. So this is the network architecture of the NERVA SMS Square used in this security assessment. The architecture consists of 2 redundant rings for the control network, and which is connected to the operator station at the bridge and the machinery control room, to the primary and backup SCADA server. The servers are also connected to the OT network for data acquisition from the cluster PLCs. So CCTV has a separate network by itself for video footages and is accessible through the operator station. So the NERVA SMS Square system is then represented using a data flow diagram to facilitate threat modeling and analysis. From the data flow diagram, we can easily identify the attack surfaces. We use the Microsoft STRIKE methodology to perform threat analysis. So STRIKE classifies and characterizes threats based on the attacker's motivation and exploit types. There are 6 categories of the STRIKE, and they are spoofing of identity, tampering of data, repudiation, information disclosure, denial of service, and escalation of privilege. For each attack surface identified, each threat category is considered in order to derive a list of threats. After the identification and analysis of threats, we perform risk assessment using Heaven's methodology. Heaven's uses a detailed representation of security levels that associates security levels to each attack surface threat pair. There are 3 steps in performing the risk assessment. The first is to determine the threat level of the identified list of threats. The threat level is dependent on the potential of attack as well as the opportunity to perform the attack. The next step is to determine the impact level and of the identified list of threats in terms of safety, privacy, operation, and financial aspects. The security level is then derived from the threat level and impact level using the security level matrix as shown. So the security level is derived for each attack surface threat pair according to the 5 security levels. So the result of the threat analysis and risk assessment are shown here. It is expected as this security assessment is done on the target system without consideration of any security measures in place. So addressing the identified attack surface threats can be done through implementation of security control measures and incorporating security requirements into the system development process with the aim to reduce the attack surface. Next, I'll be covering on the condition-based maintenance. The sense-making system of NERVA SMS Square supports the operator in adopting a condition-based maintenance regime by using algorithmic method to forecast potential failures of platform equipment. These predictive algorithms are developed and trained using data analytics and machine learning techniques, as well as marine technology domain expertise before being implemented on board. The sense-making system is deployed on an autonomous tugboat project. Data from 2 main engines and 2 diesel generators were processed by the sense-making system. A total of 273 selected parameters were analyzed. So this is a screen capture of the NERVA sense-making system deployed on the autonomous tugboat. It shows the anomalies detected and the potential failures of the machineries. There are also indications on the time to failure as well as the time to maintenance for the machineries. For the anomalies detected, there are also advisories from the decision support system on operator actions and maintenance actions. Okay, wrapping up. So I have shared on the envisioned benefits of digitalization of ship operations through the concept of DigiShip, as well as some of the works done in the area of 4.5G network connectivity for vessels operating in Singapore coastal waters. Cybersecurity assessment using STRIKEs and Heaven's methodologies for NERVA SMS Square, and also condition-based maintenance with decision support for operators. So I would like to thank you for your attention, and I'll be here to take any questions.
Thank you, Siu Ping. Any questions? Okay. In view of time, we are running a bit late. So may I invite any of, if there's any questions, feel free to approach Siu Ping later on during the tea break.